This is the Jacobian, and we're going to look in video 1 at a 2x2 matrix. This involves linear algebra. It requires a calculator if we have numbers, but the Jacobian uses partial derivatives. So we're going to have an introduction and also work on a 2x2 matrix. So the Jacobian is simply a determinant of partial derivatives, and you know determinants from linear algebra. So let's see what a Jacobian really is, because many books don't define it in plain English. It is the amount of change relative to the original plane or image. So you have an image, but you're going to stretch or shrink it, and you're also going to spin it in 3D. So the Jacobian is going to produce a value eventually, and that value indicates the amount of change, which means a shrink, an increase, and a spin, if there is a spin, okay? So the new image is an expansion or shrinkage of the original image. We use the absolute Jacobian in statistics, and this Jacobian, once it becomes a number, the only way it becomes a number is when you pick a point, x and y point, okay? So once you pick that point and you plug in, you're going to look at a specific point on the 3D plane to see how that point behaved, because the other points will behave different, because the new image, if it is twisted, not flat anymore, then the points down a slope are going to be different compared to points on a flat plane. Okay, it's a multiplication factor, it's an adjustment in double variable calculus. So if we're doing a transformation from xy to uv, so we're talking about going from xy to uv, in that transformation, we are going to use the Jacobian and a double variable calculus and a function of x, y, z, and then we get dx, dy, dz. So the Jacobian is necessary to appear in this double and triple variable integral. This is a triple variable integral. So here's an example used in engineering a lot. It's the original light, which is a circle, and how it's reflected on a surface, and you change the angle theta, the reflection stretches, and if you look at a wall at the bottom part of it, the reflection goes back to a circle again, or it can be completely elongated. So the new image is a distortion of the original image. So therefore we need the Jacobian, which is going to multiply the function x, y, z in a triple integral case. Let's look at a 2x2 matrix. We have a matrix from linear algebra. We remember that the determinant is AG minus CB. AG minus CB, I do some arrows here to help, visually see how the determinant is produced, and that's how the Jacobian is produced. I put an example of a 3x3 matrix, but I'm going to address that on video number 2 when we take care of 3x3 matrix, okay? So we're going to talk about this page on video 2, which is 3x3. Let's go to a 2x2 matrix. Well, first, let's take a look. We have a function of xy, which is xy. And another function of xy, which now is 3x plus sine of y. Now, we need to find the Jacobian for this. Don't forget that the Jacobian is a matrix of partial derivatives. It's not a matrix of derivatives. It's a matrix of partial derivatives. Now, how can we find a partial derivative? Well, the best way and the simple way is this. Put your finger here and don't let it go. That is to remind you that you're going to be looking here when you go through the first row. Once you're done with the first row, move your finger here and keep it there, and then go through the second row. This finger thing helps you when you have a 3x3 matrix, because people tend to do one cell and then they forget and move over to the second function to do the second cell. That's not it. Note that the first row is for the first function, F1, F1. The second row is for the second function, F2, F2. So, holding this, I'm going to look at the function 1, do the partial relative to x. So I take the derivative of x, y is a number. So this derivative is 1, I have the y. I'm still holding my finger here and moving over to this cell. Again, function 1, but now is a partial relative to y. I take the derivative of y, number 1, I get the x. Now, when I move over to the second row, my finger goes to the second function. I'm looking here, function 2 is a partial relative to x. Well, look at the function. This derivative relative to x gives number 3. And the derivative sine of y relative to x is 0. So this would be 3 plus 0, which is just 3. Now, your finger is still there, you're moving to this cell. It's still function 2 relative to y. This time, the 3x relative to y gives us 0. And the sine of y gives cosine of y as a derivative. So here is the matrix of partial derivatives. This is not the Jacobian yet. The Jacobian is going to involve this multiplication down, like I showed on the arrows before, minus this multiplication up. So as we go down, we get y cosine of y, minus, which is this minus, go up, 3x, and the Jacobian is absolute. So here's the absolute, and we're done. Now, if somebody gives us a point xy, I plug it. In this example, I picked point 21. So x is 2, I put a 2 for the x, y is 1, I put the 1 for this. And of course, you're going to use a calculator after you plug 1 for y, 2 for x, and go on the calculator, punch it, and you're going to get this number here. So this number here is telling us that there is a change of 5 folds, basically 5.5 folds, when we go from the plane xy to uv. On video 2, I'm going to address a 3x3 matrix, and it's going to get a little more complex.